Hi everybody, this is Cameron from Arx Research, also from Kong Cash. You might know Kong Cash because previously we dropped the first crypto cash notes that look like flexible real cash with chips on them. Since then we've been working on Halo chips. Halo chips look like an NFC chip, but they're actually very, very different. Most NFC chips are typically pretty insecure. Either they're just a link that points to something like a QR code, or their security relies on a centralized back-end service. So you have to have that chip talk to a private API to validate that the chip is valid. And of course, if that company or service or whoever hosts that server goes away, you can no longer validate the chip. None of that is true with Arx chips. Arx chips are completely decentralized, fully composable, and immutable. They come in a lot of different form factors, and in the dev kits, you should have several of them yourself, including a round tab, a hanging tab chip, as well as a Kongland Citizen Green Card, which is the card format. So what exactly do I mean when I say it's immutable, composable, decentralized? Well, the number one thing is Arx chips generate their own signatures, and these are fully compatible with Ethereum or really most chains, and you can use them immediately to do things in smart contracts. So without having to talk to some Oracle or some third-party service, you're able to immediately take a chip that you scan in the wild completely offline, validate the signature, and then on-chain use it to do some action in a contract. Likewise, they're extremely composable. You can take these signatures and you can remix them in different ways. You can use them in different services. They're ready to be used in all sorts of DeFi type applications. Typically, you'll see Kong chips embedded in things from cards to skateboards to clothing. There's lots of different ways that you can use them. For this exercise, we're going to go through an overview of how to interact with the chips and some of the software tools that we built to do that, all of which are open source. And then we're going to talk about how you can resolve to the chips. So by that, I mean, when you scan a chip, what does it do on chain? And for that, we've built something called ERS, or the Ethereum Reality Service. And I'll have my colleague Brian talk about that in a little bit. So let's dive in. As I mentioned, our chips are a lot different than other chips out there that you might find that are NFC. So we're starting to call them on-chain NFC. If you want to learn a little bit more about this from what I've already described, take a look at our mirror where we explain how other chips are effectively going to expire at some point. That's not the case with Halo chips. If we disappear, go away, get acquired, it doesn't matter. The chips keep on working independent of us. The first place to get started is really in our docs here at docs.arx.org. The docs explain more about the hardware level of the chips and how they work. So for instance, you might want to learn about the URL structure of the chip. When you tap a chip, there's a very long URL here, and it includes a lot of data from the chip. It includes the public keys of the chip, the keys that you use to sign data with, as well as in the new chips that you have, a randomly generated signature that you can immediately use to get going. So what I'm going to do here on my phone is go ahead and scan a chip to demo this functionality. I'm going to use an app called NFC Tools because it lets me grab the NDEF data from a chip really easily. So I'm going to tap on a chip here. Great. So we've pulled it up here and we see that we have this long URL record. This record contains a bunch of useful information about the chip, and I can use it to parse out this random signature as well as the public keys as I've just shown. So that's one way to interact with a chip. We call this non-interactive mode. And this generates this random challenge that I've discussed. However, there's another much more powerful way to interact with a chip, and that's by integrating the libhalo library, which I'll reference here as a second link. And the libhalo library lets you request signatures on demand from a browser. So the really neat thing about this is you're able to build a full web app, think something like a friend tech, and have it interact with chips via NFC without the need for going into a native app. And obviously that's super powerful because you don't have to get App Store approvals, you don't have to update native apps. So for that, I'm going to go ahead and demo a bulk chip scanning app. So what we've done is loaded up libhalo demos on my phone here. You can see on the right side. LibHalo demos is a really nice way to test out just simple signatures using a chip. You can find it at halo-demos.arx.org. LibHalo itself is a great resource to take a look at. So the LibHalo repo has a lot of documentation that you're not going to find in the docs pages, specifically on how to integrate LibHalo into all sorts of different applications, like an HTML web app, a React app, even React Native mobile apps. The neat thing about LibHalo is that you can use it across a bunch of different transports. So you could even use it in a desktop command line interface using a USB scanner. It's incredibly powerful. So back to my phone here, let's go ahead and load up the simple signing demo. What's happening in this demo is we're taking a string and we're hashing that string and then having the chip sign it. So we'll take this random string here and we'll go ahead and tap the chip. Boom. The chip has now taken that message and, that digest, the hash of the message, and gone ahead and generated a signature from it. And below you can see the Ethereum formatted signature, the 0xE64. The really neat thing about this is we can start to imagine signing all sorts of messages. So say for instance in this simple demo, instead we were to sign the message of a recipient of an NFT plus a recent block hash. And we could feed that into a contract, and that contract said, I know this public key, and I'm going to mint an asset to it. We'll get to a practical example of that in a second. But one of the things I want to show with the LibHalo demos that's really neat is how to use it away from your mobile phone. As I mentioned earlier, there's a bunch of different transports that you can use with LibHalo. One of the more interesting ones is the LibHalo Gateway. The LibHalo Gateway is a really powerful way to get signatures from a Halo chip onto a desktop without having a custom USB scanner. So say for instance you want the user to interact through a web page, yet they need to get a chip signature. They can do that using the LibHalo Gateway. So what we're going to do here is initiate a gateway session. We bring up a QR code, and we'll scan that QR code from the phone. What we've done now is we've created a session linking the phone and the desktop version through the Halo Gateway. And we can confirm the request from the Halo Gateway, which is to sign this message. So again, confirm, tap the key, and boom, we have the result piped through in JSON for us ready to use in our dApp. So we've talked a lot about the nuts and bolts of getting signatures from chips. Why don't we look at some practical examples? One of them is ERC 5791. ERC 5791 is a proposal for physical backed tokens. The idea is that anything embedded with a chip can be transferred on-chain only through signatures generated by the chip itself. So for instance, if I have an Azuki Golden skateboard, I can only transfer that thing on chain if I can tap the skateboard itself and get a valid signature from it. I can't resell it on OpenSea, but it gives a really strong link that I'm likely the holder of it because I can generate signatures from the chip. You can take a look at the implementation proposal here, as well as learn more at pbt.io. The PBT smart contracts are a great place to understand how you might enroll chips against an asset. So in this case, there's a mapping of chips to a mapping of token IDs. Again, this is one example of a contract you might come up with. You could come up with a really simple NFT minter where any signature from a chip allows you to mint an NFT. You can come up with a simple wallet where a chip allows you to transfer assets. There's all sorts of things that can be built on top of chips, but it's worth mentioning the PBT because there's a lot of great code examples here in the Azuki repo.
Hey guys, Brian from Arx Research here. Cameron gave a really great overview of our chips and how you can use them and interact with them using desktop or mobile. I'm going to give us an overview of the Ethereum Reality Service. So the Ethereum Reality Service serves two main functions. First, it provides a chain of custody. So from manufacturer to the project or entity that creates an experience around the chips to the ultimate end user. And second, it also allows us to have kind of a public database of all the services that are attached to a chip. So these services can provide new experiences and tie new experiences to the chip. So I will start walking through kind of the participants in the system. As mentioned, there's manufacturers, which is Arx Research is one of those. So the ones that create the chips, and then they actually enroll them into the Ethereum Reality Service to kind of create that first step in the chain of custody. Then we have what are called TSMs. TSMs are, we take this from kind of mobile lingo, they're trusted service managers. And what they would, in the system, what they would do is maybe create a project around a set of chips. And they would enroll all those chips in this project and attach, certain experiences then to that chip. And then from there, they may send that chip or sell those chips that are embedded in goods to an end user, or what we would call chip owners. So these chip owners would be, essentially those that may purchase an item that has a chip embedded in it. They're free to, kind of use that chip in any experiences tied to the chip. They can obviously transfer it as well to new holders. And then we finally have service providers. And these are kind of pretty coupled with the idea of a TSM. We imagine a TSM would have some of their own services that they would tie to a chip, but this is ultimately an open resource. So anybody can create their own services, and the chip owners can decide to tie that service to their chip as well. So then this way, you can start adding more and more powerful functionality to your chip over time. To give a really brief architectural kind of discussion here, we have a series of registries. The ones that are probably the most important for your purposes are the chip registry. This is essentially a big ERC 721 contract, but we've modified it and created what we're calling PBTs. And this is going to store, a lot of the information about the chip that's not, hosted in IPFS or placed in IPFS is going to be stored in this registry. And this is how the registry you interact with if you want to transfer the chip, things like that. The manufacturer registry, this contains all the information about chips that are enrolled in the system. ERS registry, this is very similar to ENS. This is going to be just kind of essentially a chain of custody through these various root names, very similar to set up very similar to how ENS is set up. And then finally, you have this services registry, and this is where people can come and enroll their own service that links to, it could be a IPFS hosted service, it could be a centralized service, it could even be a different contract address or anything like that, right? So this is kind of a high-level architecture of the system. And next, I'll start showing you how you can actually interact with the system using our ERS scripts repository. So now that we've learned a little bit about the ERS system, we are going to start by creating a service. So a service we can ultimately tie to chips that we're going to enroll into a project in the next step. So first, we'll talk a little bit more about what a service is. So a service is essentially a set of records, and these records can really contain anything. We have a couple special records. These are, stuff that the system kind of, in one way or another, acknowledges. So the first would be a token URI. So you can tie a token URI to a chip within every service. There's also a token URI tied to a chip at kind of that chip registry level. The chip registry token URI does override anything tied to a service. However, if the token URI is not present on the chip registry, then it defaults to whatever is in the service. And then the second one is the content app. And this is probably the more important one. When you tap a chip for the first time, the first thing that will pop up is that chip's content app. But ultimately, we could make this any form of content, and it's just up to the client or website to kind of parse and analyze that content. So it could be a smart contract address. It could be, some centralized website. Could be an IPFS website. Those sorts of things. And the kind of the whether the website or the contract address, that would be considered the content within a record for that service. And then you also can specify as part of that record whether you want to append the chip ID on the end. And the reason we do this is there may be some things that you want to be unique to a chip. So this could be the token URI, for example, or there may be some resource that you want to share uniformly across all chips. And in that case, you don't really want to append an extra ID at the end, this extra chip ID at the end. You want it to just all chips to redirect to that singular URL or IPFS instance, whatever it may be. Then there's also this concept of primary versus secondary services. So the primary services, so you can have one primary service and you can have any amount of secondary services tied to a chip. So that primary service, when you tap the chip, the content app of the primary service is what will pop up. But you can imagine there may be clients that would also, when you tap a chip, can bring up a list of the secondary services that the chip is enrolled in, and you could navigate to those services via that client. So I'll do a really quick example of how you create a service on chain. This is the ERS scripts library. I should say, this is the ERS scripts library. It's a repo of essentially CLI functions that can be used to interact with the ERS protocol. Here we have we're going to, this is all being done on localhost for now. We are going to enroll the service. So we've named the service Arx Dev Connect. We have the content here. Later on, you'll get to see what that content is. And then we've decided not to append an ID because this piece of content we want to share across all chips that end up being attached to the service. So now we'll press enter. And we'll see the transaction submitted on the chain here. And now we have the service Arx Dev Connect. It's created on the service registry, and this is the service ID. So we'll have to make note of that service ID, and we will next create a project. Great. So now that we have a service created, we're ready to try to tie that service to a set of chips. So the set of chips we can think of as like a project, right? So, I have 3 chips right here, 1, 2, 3, and these chips we're going to enroll in a project. Now you can envision them being embedded in a piece of clothing, perhaps a piece of artwork, that sort of thing, right? And now we are going to, we're going to tie some experience to this and send it out to end users. So first thing, to add a TSM, it has to be done via governance. So we've already added a TSM under which you can enroll your own projects. And we have a separate smart contract that manages that enrollment process. In terms of adding projects, there are some things some pieces of information you have to provide. A lot of this will be abstracted away in the scripts that we've created, but you do have to name your project, and this is part of going to that ERS registry and string of authenticity. Is now we'll have we have the name root of the TSM, which would be us, Arx Research, and then you'll have the name of your project now appended in front of that in kind of the chain of custody. As part of this as well, you'll have your own project registrar that's deployed as part of interacting with our manager contract. You'll have to create a Merkle tree and hence a Merkle root that proves inclusion of these chips in a project. And this will be done by the script itself. There's a couple other things that need to be, created. All of this is managed by the scripts that we have. One thing I'll point out is the ownership proof. This is essentially proof that the project owner, had custody of the chips at the time of enrollment. You'll be signing this project registrar address that's created. The project registrar is created through via create2, so we can predict the address as part of it, or the address that comes out of that transaction, and then we'll sign a message, and that's validated in ERS. And then there'll be this claim data URI, which is necessary to actually for the users to claim the chips, right? So let's pop over to ERS scripts, great. So now we have, before you had to, you had all these different inputs you had to put on the command line. There's too many inputs for this, so we're going to put them into a separate file, which can be found in the task params folder. You'll want to copy the default file and kind of create your own inputs. Here we're naming our project Dev Connect Demo. We'll have a link to, you'll want to link to the chip data. The chip data is, you'll be able to find that by going to the manufacturer validation data. Now this is, when I enrolled the chips in ERS, I also created posted that data to IPFS. And so you can grab this chip data, parse out the different pieces, data fields that you need to create an array of chip data, which you can place in this chip data location. I'm not going to specify a token URI, but you can do that very easily. This is the service that we created in the last step. Great. So now that we've gone over this file, we're going to be ready to actually execute the transaction on chain. So this is actually pretty simple. Now that we have the kind of params file set up, in this instance, I want to specify to make sure that the project enrollment files are posted to IPFS. This makes it easy for users to then be able to actually do the claim portion of or make it easy for them to claim their chip. So here I'll just run this script. I'm also going to need my phone for this. And here we are going to put up a QR code. And what this QR code does is it links us to the Halo gateway, which you can see here. And now I will go through and sign these custody proofs or ownership proofs. It takes 2 taps usually. And then now we'll go, and now this is showing that I currently also have custody of one of the chips. The custody proofs, in theory, those could be, if anybody has access to the chips, they could create these custody proofs. But this portion right here requires knowledge of certain parameters at runtime. So you'd actually need one of the chips in your possession to be able to submit as part of this project. There we go. And great. Now our project has been created. We can see that the data for the project was posted to IPFS right here. So if we now go to that root, here we go. And now you can kind of see what these are all the chip addresses, essentially, what we call chip IDs, but it's really the address of the first private key slot on the chip. And here you can get all sorts of data. So we have this enrollment ID is the manufacturer enrollment. This right here is the project registrar for the chip. So when you go to claim the chip, you actually have to call this address right here. This is all data required to claim the chip. So we have kind of like the index in the tree, the service ID, which we created in the last step. Here's the URI, which is kind of a dead URI right now. And then we also have the Merkle proof right here. And then alongside that, we also have, these are kind of the TSM certificate is the chip ID signed by the project public key for the project, or the private key associated with that project public key. Then the custody proof is that project public key signed by the chip, right? So you obviously need to have custody of the chip to sign that transaction. So this allows us to kind of make sure that at some point the person who created the project had custody of the chips. Great. So now we have created a service, enrolled our chips in a project, and now I'll show you how to claim one of those chips from the project. So what does claiming do? Claiming essentially allows you to kind of complete that chain of custody. It's like, now I own this item. I can claim it and show the world that I own the item. And that will be kind of etched onto the blockchain forever. And then it also allows us to kind of like instantiate this primary service and like kind of officially tie it to the chip by kind of enshrining that on chain as well. Additionally, this allows you to start adding some of these secondary services we briefly mentioned before. So you can start putting on, adding different services that you want to tie to the chip, whether it's some other kind of like funny meme that you want to tie to the chip, or it could be like a ticketing service, like that sort of a thing, right? So how to claim it? I think I mentioned this very briefly, but you have to go through the project registrar for the project to do that. You can always find what that project registrar is. You can go to the IPFS, post kind of the project enrollment files, post IPFS. Here, this is where the project registrar is. And yeah, so now we can go back here. So that's where you would find where the project registrar is. Again, there's a whole host of data here. We will be able to, the script will grab this data from IPFS and organize it so that it's pretty easy to actually claim the chip. Let's just go ahead and do that right now. So you briefly saw this file. I'm going to name my chip Brian after myself. And then we have the chip claim data location. So this is what was posted in the last step to IPFS. Then you have the manufacturer validation location. This is what was posted by the manufacturer when they first enrolled the chip on chain. Great. And now that we've gone over the chip claim input parameter file, let's go ahead and claim the chip. Doing this on localhost. Likewise, to project enrollment, we will need to execute some. We'll have to first pull off the chip ID from the chip itself, and then we'll have to sign a message that kind of proves ownership of the chip, kind of at runtime, so to speak. So when the chip is actually being submitted, or when a message is being submitted on chain for the chip to be claimed. Let's do this. And we'll have another QR code pop up here on my phone. So now we'll pull the chip ID off of this. And now it's posting the project enrollment data to IPFS. And now I will sign this next ownership proof to kind of close the chain of custody, so to speak. And bam, now we have claimed the chip. And next I'll do a really quick demonstration of how the chip can be resolved. Great. So now we have claimed our chip. The next thing I'll promise you is just to look at how to resolve the chip, or really a discussion of resolution. We're running everything on localhost, so it's right now. So we won't be able to give you the full experience. But typically, what resolution entails is if you tap the chip, we've embedded kind of a environment or a URL in that chip. So when you tap it, it'll go to that URL, and in that URL, we have logic at that end that then helps resolve the chip based on data that's been stored on chain and off chain. We do this resolution via EIP 3668, which is also known as CCIP read. Essentially, what happens is you tap the chip, it goes to the embedded URL. In that embedded URL, we perform a CCIP read call to the chip registry. When it does that, it will bubble up a revert, and in that revert, there will be some information. And the client catches that revert, pulls out the information it needs, one of which is the location or the endpoint to call to get manufacturer and project enrollment data. Now, what we have are these ERS gateways that are constantly indexing any added manufacturer enrollments or project enrollments. So you call out to one of these gateways. The gateway will then return the data, and the client that calls out will then submit it back on chain to the chip registry. So essentially what we're doing here is we're calling to the chip registry to ask it, like, okay, what do we do? And then the chip registry says, okay, go look for data here off chain. And then that location returns some data to you, and then you pass it into the chip registry, which then validates the data that was stored off chain, right? So we can't necessarily fully trust data off chain, right? So we need to do some sort of validation on it. So when you pass the return data back into the chip registry, we validate it. And if all the validations check out, then it will resolve to the primary service that's associated with the chip. In this case, since we've claimed the chip, that whole thing doesn't even happen. All we do is tap the chip. The chip registry recognizes it as claimed and just spits you right out to the primary service. If the chip had just been enrolled in the project but hadn't been claimed, then that whole callback flow would happen, but it would still spit you back to kind of this primary service. But it's not going to, it'll be a little bit longer, because you wouldn't have claimed the chip. And then if the chip hasn't been enrolled in any project at all, it would spit you out to what's called the manufacturer bootloader app. And this may just be an app that can be used if you're a project to enroll chips, however it may be, however the manufacturer of the chip wants to set it up. But the idea is if the chip is enrolled in ERS, if you tap it, it will always resolve. And so here's a sample of that. We've claimed this chip. So the chip that we claimed, this is that URL that Cameron referenced in the first video. And now that we've gone through everything and claimed it, we can resolve to this URL, which will then go to happy hacking.